In this video, I'm going to introduce a couple of ideas for simplifying your work with Taylor polynomials, and then I'll go through an example illustrating them. So here I have a partly filled in statement of the facts that we're going to use. So suppose that you know the Taylor polynomials for two functions, f of x and g of x, and you know the Taylor polynomial of f to degree n and the Taylor polynomial of g to degree m. And those are both Taylor polynomials about x equal a. So if we call the Taylor polynomial of f t superscript f sub n of x, and the Taylor polynomial of g t superscript g sub m of x, then if we take the composition of f and g like this, we get a new function h, and we can use this shortcut trick. Instead of taking derivatives of the composition function, we can take the two Taylor series and just write down the Taylor series for f of degree n composed with the Taylor series of g of degree m. And because this one here will have a highest power m, x to the m, when we plug it into the Taylor polynomial of f of degree n, the very last term in f, or the Taylor polynomial of f, will be x to the n, and the x gets replaced by a polynomial of degree m, so the total degree of the result is going to have degree m times n. Okay, and then there's a similar thing that you can do for products of functions. So if we take the product of f and g to make a new function k, then the Taylor polynomial of the function k, it'll have degree n plus m, because we take a product of a k, of a polynomial of degree n and a degree m, and the highest power on that will be the x to the n times x to the m product, which will have degree n plus m. And so what we do for calculating the Taylor polynomial is we take the Taylor polynomial of f and we multiply it by the Taylor polynomial of g. So those are just quick shortcuts. And so just as a quick example, without doing a whole lot of work on them, e to the x is approximately 1 plus x squared over 2. Let's say we go to degree 2. And 1 over 1 minus x is approximately 1 plus x squared. So if we wanted, for example, the Taylor, this is about 0, right? If we wanted the Taylor polynomial about 0 of e to the 1 over 1 minus x, then we can just plug 1 over 1 minus x's Taylor polynomial into e to the x's Taylor polynomial. So here we're replacing the x with 1 plus x squared, and then a half 1 plus x squared, all squared. And then we can do all the calculations to see what that is term by term, but that gives you the idea. And then e to the x, if I do a product of e to the x with 1 over 1 minus x, that one just requires that we take 1 plus x plus half x squared and multiply it by 1 plus x squared. Okay, so with that in mind, let's try this example. So suppose we know that e to the x has a Taylor polynomial of degree 4, given by this expression here. Let's calculate the Taylor polynomial for x e to the minus x, about x equals 0. So the Taylor polynomial of g, and here I'm going to leave the degree, well actually we're sort of, it's sort of hinted and it's kind of cooked up to work just the right way, but you will see in a moment that it does work out the way we want it to. So the Taylor polynomial for g is going to be, and please don't get confused by the fact that I used f and g over here in this example. These f's and g's are not the exact same. What we have in this example is we have a product of x and e to the minus x, and then e to the minus x itself is a composition. So we're going to use both of these facts here in calculating the Taylor polynomial of g. Now the other fact that I'm just going to trust you can imagine or see is that the Taylor polynomial of the function x is, well, if you go to high enough degree, will be just x. In fact, for any power function, x to the n, if you look for the Taylor polynomial of high enough degree, in particular degree n or higher, it is just the function itself. So here when I take the product, I'm going to take x multiplied by, and now here I'm going to have the Taylor polynomial for e to the x, which is 1 plus, and normally for e to the x I would just write down x, but it's minus x is plugged in there, so I'm going to use the composition. And the Taylor polynomial of minus x is minus x, at least for degrees greater than or equal to 1. And then plus 1/2 minus x squared, and we're going to do it up to 4, so this is going to be plus 1 over 3 factorial minus x to the 3, outside the brackets, plus 1 over 4 factorial minus x to the 4. And so we can simplify all this down to write a term-by-term Taylor polynomial. First, let's take care of all those minus signs. We have 1 minus x plus 1/2 x squared, because there's 2 minus signs in that product, plus 1 over 3 factorial x cubed, but there's a minus sign from the minus sign cubed, so we get rid of that, turn that plus into a minus, and then plus 1 over 4 factorial x to the 4. And now, I changed the function that I was using here, so let me actually modify that, of degree, and I'm going to put a question mark here because it's just going to fall out for us, of degree something or other, and we'll see what we end up with. So now multiplying through, we can see what we're headed for. That's why I modified that statement in the question. Plus 1/2 x cubed minus 1 over 3 factorial x to the 4 plus 1 over 4 factorial x to the 5. So here, if the question had asked for a polynomial, Taylor polynomial of degree 5, then this would have been the answer. Now, if it had asked for the Taylor polynomial of degree, let's say 14, then we would have to use a lot more terms here. We couldn't use T4 for e to the x. We'd have to go all the way up to, let's see, what did I say? Degree 14. So we'd have to go all the way up to degree 13 here, and then this x would give us 1 more degree. So that's why I changed it to 5, so we didn't have to go on forever. But in a lot of these problems, the degree may be quite high, but because, for example, if this was a higher power of x, you would end up having a lot of terms missing, and you'd have very few terms in your expression all the way up to, let's say, in the case of the example I had before I modified it, could be, degree 14 might not be that difficult to calculate. Okay, so that is a simple trick or a simple method for simplifying your calculation of Taylor polynomials.